Hello, 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 everybody. I think it's 1 second and go. I'm good morning, and I'm Michele Fiorentino, University Polytechnic University of Bari, Italy. I'm glad to chair this fantastic session about learning and training in industrial context. Thank you for coming. I think we have a lot of cool papers to listen, and this is the first one, which is also I've been awarded. I've been nominated for Best Paper Award, and the title should I evaluate augmented reality system in industrial environment, investigating the effect of classroom and shop floor setting on a guide assembly. Per Kristensson from University of Cambridge. Take you to the podium, thanks.
Thank you very much. I'm very happy to be here. And long story short, this paper is looking at the verification and validation environment when you try to take AR into industry. So where you have a classroom environment to the left, that's the actual classroom environment we used. And we have the manufacturing environment to the right with machines, noise, etc. Does the actual environment have an effect? Short answer is yes. The task itself also has an effect. So we actually tested 2 different AR-guided tasks. These are manual assembly tasks with AR guidance, very popular topic in the AR literature. The gearbox assembly task was deliberately designed to have a lower complexity. And then we also had a control station assembly task that had a higher complexity. And just before I start talking about the method and results, I want to say, like, what's going on here? Why do we care about this? Well, really, when we try to build a system, right, from a design engineering point of view, we do task clarification. We try to understand the best problem, right, and the problem we should tackle. We do conceptual design, so we figure out what we want to do, the functions, and then we translate them to function carriers, the hows. Once we have identified a promising concept, we do embodiment and detail design, and we build a system. This system then has to be verified, so we have to ensure that requirements are met, and validated, right? Is it fit for purpose? So what does this verification and validation mean? Well, if we don't verify and validate the system, right, in the intended environment, we kind of have a problem because the system is going to be deployed in a deployment setting. So the environment may or may not have a huge influence on the success of verification and validation. And in addition, when you use any system, people try to achieve their goals. People will do anything to achieve their goals. It's called appropriation. So the users we use, the tasks we tell them to do, and the practice that's going on the shop floor, all of this stuff affects the system and affects verification and validation. We began this paper by doing a systematic literature review. I will not spend time on the systematic literature review. It's in the paper. I would only tell you that only 14% of studies were actually carried out in non-lab settings, so a very small minority of studies. And a maximum of 30 participants had some industrial background, emphasis some industrial background. So what we want to do here is to check, well, you know, what about what's called construct validity? Are we actually giving people appropriate tasks that actually make sense and measuring the right things? And what about ecological validity? Are the results actually generalizing to the settings where we want these systems to be successful, that is, in industrial environments? So in terms of method, we recruited 32 manufacturing apprentices. So these are people who actually have manufacturing experience, but they're still in training. In the design, we had a between subjects variable. That's the environment itself, the shop floor, manufacturing shop floor versus a classroom setting. Participants were very familiar with both of these environments, by the way. And we also had a within subjects variable, and that is essentially the assembly task complexity, so the gearbox and the control station assembly. We randomly assigned people to an environment. All people did a gearbox and the control station assembly, and we counterbalanced the conditions there, and then we took a whole bunch of popular ISMAR, IEEE, VR, quantitative and qualitative measures during the study. All of these measures are in the paper. I will mention some of them here later. And we also did some triangulation, so we also did interviews to try to figure out what is going on in people's head as well, not just what they are exhibiting in terms of measurable behavior. The task itself was a gearbox assembly task, as I said, and a control station assembly task. We can see what the people were assisted with virtual instruction panels using the HoloLens 2 optical see-through heads-up display. This is the gearbox manual assembly. Here we can see next and back buttons for navigating in this virtual panel. And this is an example of an automatic step verification visualization. I think this is fairly standard stuff, and we're not claiming any novelty whatsoever here. This is the control station manual assembly, and the control station manual assembly actually required also QR code as a reference point because it's a little bit more complex task, which I will get into a bit later. In terms of settings, so the settings here are clearly important. So we had a classroom setting that emulates a typical lab environment, and this is a familiar setting for these people. They actually are in the classroom and they learn in this classroom. But the participants were not used to carrying out manual assembly tasks in the classroom. The shop floor was an actual industrial and manufacturing environment with workbenches, equipment, industrial activity in the background, and so on. And participants were familiar with both settings. In the paper, we really try to characterize the qualities of these environments because this is obviously important. And as you can see, there is a lot of different qualities that affect different environments. I will not spend time on it in the interest of time here, but this is in the paper, and I think this is quite interesting to think about, actually, when it comes to lab settings versus industrial settings. Long story short, I want to talk about results quickly because I want to talk about the implications a bit more. In terms of results, shop floor, right? Doing this task in the shop floor resulted in shorter task completion time. So anything I say here is going to be significant. So the figure you should look at is the top figure here. It shows task completion time, and we have ranked participants in either condition by performance. So any participant number that starts with a C is from the classroom, and any participant number that starts with an S is from the shop floor. And as you can see, at every possible ranking position, people are doing the task faster on the shop floor. Shop floor also resulted in lower error counts, as you can see here to the left. And to the right, we have actually categorized what actually went on in terms of errors. I will actually revisit this in a couple of slides in the future, so I will not talk about that table for now. The shop floor participants also reported higher flow levels, so we took a bunch of qualitative measures. I will only report a few headline findings in the interest of time. There's more in the paper. But people generally felt they were more in the flow in the shop floor than in the classroom environment. And again, same tasks, right? No, same task, same procedure. So let's look at the task, right? The construct validity. Like, what about the gearbox assembly task, which is a little bit artificially simple. It's not a task of the complexity you would normally do in an industrial environment. Well, the gearbox assembly task resulted in shorter task completion times. And now I want you to look at the bottom here. To the left, we see the gearbox. To the right, we see the control station. The figures look the same. What's going on? Am I trying to trick you? But look at the scale of the vertical axis, and you will see that the gearbox clearly was faster than the control station task. The gearbox assembly task resulted in lower error counts. And if we look at the error counts, we can see that at the control station, for the control station assembly task, there was a lot of errors going on. And what's interesting with some of these errors is that they are basically reversal errors. We sort of get things upside down or wrong direction kind of things. And I will talk more about that in terms of implications, trying to explain why did this happen in the control station task, and why did it happen more in the classroom than in the manufacturing environment, which is really perplexing if you think about it. There's no reason whatsoever why that would happen. In the gearbox assembly task, participants also reported lower perceived task load. In other words, not only were they able to do things faster and more accurately in terms of quantitative performance, they also felt that the tasks weren't as cognitively demanding. What I really want to go into is the implications. So if we try to do any sort of study, right? So there's been 1 million AR studies supposedly supporting industrial tasks, right? And if you do any sort of empirical AR study or study in general, you have to think about construct validity. Am I measuring the right things, and am I giving people the right task that is actually sensible? Internal validity, can I actually draw causal relations out of my data? In other words, does my manipulation of the independent variable lead to measurable changes in dependent variables that I can believe in? We also have to think about external validity. We need to generalize our results to other studies. And we need to think about ecological validity, right? Even if we generalize to other studies, that is actually generalized to the deployment environment we actually care about. And we have to think about study heterogeneity, so we can actually do meta-studies and actually compare studies. And finally, we have to think about replicability. Can people replicate the findings? In terms of this, our systematic literature review, again, details in the paper, and I will not say much about it, actually fully or partially addresses internal and external validity, study heterogeneity, and replicability. It actually does a pretty good job, right? So it's not bad, right? We're not saying everything is a disaster here. It's not. But it does leave these two, construct validity and ecological validity. And I think industrial environments is just this particular kind of application where you really have to think about this, unfortunately. So I do a lot of text entry research, and there you can get away with not thinking so much about ecological validity. But here you really have to think about it, because what our results are showing is that the setting itself significantly and quite dramatically affects several measures, right? So if you're showing results in a lab or in a classroom setting, it actually might very well fail to generalize to deployment environments, and that's quite worrying. And the other thing is construct validity. So what we also show is that this kind of the task itself has a significant result on the findings, which sounds obvious, but a lot of people use simplified assembly tasks. And the problem with simplified assembly tasks is that they are not representative of the complex assembly tasks people have to do, where people get stressed, they get anxious, they doubt themselves, there is pressure to perform, and so on. Oops, why did that happen? Okay. So let me zoom into ecological validity, so the influence of the classroom and the shop floor settings. So we try to explain why is there actually a difference in the settings. So one explanation, what we are conjecturing, we are not proving definitive evidence here, but as a conjecture, is the familiarity with the environment, right? So prior exposure to, why is this moving around? Anyway, prior exposure to familiar manufacturing environment with noise and constant movements provides a sense of reassurance, actually, and decreases stress. And there is some evidence in the literature, but not in the manufacturing literature, but in the nursing literature of all places, where we've actually demonstrated this effect. And we also have some interview data that corroborates this conjecture. Again, more details in the paper. The other explanation is that people have different associations with different environments. In the classroom, people feel that they are learning, and they have time to learn and time to reflect. In the shop floor, it's performance, right? You should perform, and we can also see the literature suggests that the learning environment is associated with help seeking, right? So people want to seek help, and we did see this because only in the classroom did participants seek affirmation from the experimenters. The third explanation is this idea of choking under monitoring. Observational pressure makes people perform below their actual abilities. And there is evidence in the literature that if people know that they are performance evaluated, that does increase self-awareness and self-consciousness. In addition, this occurs both in real-world lab environments and manufacturing environments, or whatever environment you're testing in. But you can actually alleviate this monitoring pressure by distracting people. And the shop floor environment is highly distracting. There's noise, people moving around, lots of stuff is happening, and so on. And this conjecture is corroborated with interview data. In addition, this idea of choking under monitoring tends to induce performance anxiety. But performance anxiety is also linked to demographic characteristics, but we checked for that, and the demographic characteristics did not explain any performance anxiety. In other words, it was the environment that induced this effect. And if we look at the error analysis in the paper, which details this, we can also see that the types of errors like the reversal errors and doing things in the wrong way, etc., is exacerbated in the classroom. In terms of constructability...
Sorry, Perola, can you go to conclusion,
quickly,
please?
Yes, very, very quickly. So in terms of construct validity, first of all, we can show that both quantity and quality data shows that task complexity influences performance. And in terms of construct validity, the second point here is that the ease of comprehending instructions. So the control station assembly task had more steps, higher variety of components. Interview data corroborates this. And in addition, we had to fill it with the QR code. So the message really is that the verification and validation environment really has a very significant measurable effect, and also the task, right? So the task has to be complex enough to be representative of real industrial tasks, and also these systems have to be tested in real industrial environments, or the findings may not generalize. Thank you very much.
Thank you. Well, we have time for a couple of questions from the audience. So, yes.
Hi, Daniel Roth, TU Munich. Very interesting talk. I think it was a bit in the context of your comments and guidelines, I would say. But I think you've got one important thing, that is the tester or the sampling target group, right? So I think it's extremely important that you test with your target group or as close as possible to your target group. I think that's a tremendous difference to people in the lab.
I agree, and this is something the literature has actually done to some extent, but that is absolutely also a factor, right? But all of these people had manufacturing experience, so we can't draw any conclusions about that effect, but I would imagine it would be enormous.
Just on your point about the choking under observation, which I think is a Hawthorne effect, isn't it? Basically, you behave differently if you understand you're actually being observed, right? Did you look at, or did you try doing these tests over time to allow people to kind of get more familiar with the environment and begin to forget that they're actually there? And did that change their behaviors?
So that is an interesting thing. So, well, I don't remember the exact duration, but we did take some time to do this study, so there was time to familiarize themselves. But another point is participants, and I want to emphasize this, were well familiar with both environments. So these were not unfamiliar environments for them. It wasn't like we put them in a completely different classroom they've never seen before, or a manufacturing environment we hadn't seen before. I would imagine there is an effect there.
Yeah, it's not so much the familiar with the environment, it's forgetting that they're being watched. So in other words, let them kind of do the task and forget that they're being studied.
Right. I personally believe that they were long enough. It's difficult to say, of course. Everything should be replicated, but it wasn't like a very brief kind of 5-minute task, so people had time to...
Anyway, it's great work. Really good work. Thank you.
Thank you. I think we are done. Thank you very much. Let's go to the next talk. The next talk is called Immersive Authoring by Demonstration of Industrial Procedures. Author, Lucchas, Ribeiro, Skreinig. Sorry, I did it. So.
All right, thank you. Thank you again. My name is Lucchas Ribeiro Skreinig, and I'm here, as mentioned, to introduce our research on behalf of myself and my co-authors Peter Mohr, Blanca Berger from the Graz University of Technology, Markus Tatzgern from FH Salzburg, Dieter Schmalstieg from University of Stuttgart, and of course Denis Kalkofen, also from Graz University of Technology. This research is focused on the improvement of the creation of immersive instructions for complex industrial processes using virtual reality to make content creation more intuitive and more efficient. Traditional methods of authoring maintenance or machine instructions can be a long process. The creation of written manuals is slow and multidisciplinary, and often requires the creation of illustrations or animations from CAD data, using 3D modeling or animation skills to create image or video-based content, as well as text for paper manuals or websites. Yes. Another problem with established methods of manual creation is that authors often lack hands-on experience or access to real machines. In turn, engineers with access can fail to provide clear instructions or content requiring multiple rounds of communication with technical authors and writers. This tedious and time-intensive communication can make authoring manuals a slow and iterative process. To address these challenges, we present a virtual reality authoring tool, which is designed to streamline the creation of immersive instructions for industrial processes. Experts can interact directly with 3D models of industrial machines in VR using a head-mounted display with hand tracking capabilities. This enables interaction with machines using natural manipulations and captures complex hand motions that would otherwise have to be explained or animated in great detail. Experts can create motions and manipulations without the need for programming or animating skills. And interacting with machines in a realistic, full scale helps authors also better understand spatial relationships, which is definitely an important aspect of authoring these manuals. Using models generated from real CAD data, our system allows users to manipulate virtual machines realistically or near realistically, as the virtual representations mirror real machines about as closely as you can get. Our system records detailed hand movements, as previously mentioned, and machine part manipulations. and offers options to capture additional content, such as gaze data or speech, for adding more detailed comments while the experts are manipulating the virtual machines. Yes, here. We implement a feature to manipulate individual components or hierarchical subassemblies using the data from the CAD models. This allows authors to realistically manipulate parts that are connected to one another, and as this data is already present in the CAD models typically, this is basically a free addition. In addition, work steps are automatically segmented from recorded instructions. Our system analyzes the recordings that the authors perform and groups frames in which interactions with the machine occur. We additionally introduce a user-friendly interface for post-processing these work steps and segmenting and further refining the segmentations that happen automatically within the VR environment itself. Visual cues, as you can see, include activity clouds and visual links to the manipulation interface that help the authors locate the manipulations in a room scale environment, as navigating through complex instructions could otherwise become difficult. Using the three-dimensional, or the 3D rather, hand and machine part movements that our system records, as well as additional content, as mentioned, as like gaze data or speech, this enables also various output modalities. The recordings can be used for, for generating immersive training sessions, virtual reality training sessions, or adaptive guidance using the segmented steps, as well as various formats compatible with already established instructions, such as screenshots or videos or animated avatars, as well as free viewpoint dynamic experiences that can be created using the recorded movements. Yeah, here's just a quick avatar that was animated using the head and hand poses that we captured. Anyway, to evaluate the usability of our tool and its feasibility for productive deployment in an industrial setting, we performed a qualitative assessment conducted with 4 experts in technical writing and training employed at a global engineering company. These experts had between 7 and 25 years of experience, and we interviewed them to find challenges that they currently experience in authoring manuals. Our approach included an exploratory interview with the experts to identify these pain points and challenges in currently established authoring workflows, followed by a demonstration during which the experts were actually given the virtual reality tool to test, to work with, and they provided their feedback while using the system itself, while just exploring the space and the functionality that our system provides. They were asked to comment on their experience and the various functions they discovered for themselves. After this demonstration, we conducted a reflective interview to discuss the potential of integrating this system into their established workflows. Our evaluation shows that the improvements that our system implements to their established workflows raise its potential for real integration into their productive authoring work. The professionals are receptive to adopting such a system and acknowledge its usability. For example, they mention that it has a significant time-saving potential for content creation when compared to 3D animation, or you having to manipulate these CAD models in software that is otherwise clunky to use. They also highlighted that this would introduce better communication between the teams of the authors and the engineering department, as recording a process or a problem would take, one of the experts said it would take them half the time to show the problem than describe it. The authors also praised our system as it was intuitive to use without needing instructions. We gave these experts barely any intro to what to do, and they quite naturally managed to find out how to use it. And in addition, they praised that the natural interaction improved their expectations, as it was easier to find problems or describe processes that would be difficult, as they could see more or less how it would look like in a real setting to manipulate these machines. In the future, we intend to also include, they also said that they would like to include this for training purposes, as often they training can be done offline, or rather without having access to the real machines. And they also, again, said that they would like to introduce content to the existing workflows that could be viewed from interactive viewpoints. In summary, our system addresses documentation authoring challenges as found by our interviews. We endeavor to simplify the procedures that are most important to the industrial experts, as mentioned before. Our system can improve the clarity and communication between teams. It enables fast content creation and detailed movement capture that otherwise would require more effort by the authors. And in future, we also intend to expand this to an XR environment where we can apply the captured instructions to real machines and enhance traditional training. That was a bit short, but thank you for listening. You can find more details on the project page in the full paper, and yeah, thank you.
Thank you, Lucas. I think we have good time for 2 or 3 questions from the audience.
Hi, Lucas. Cool work.
Thank you, John.
I expect it took a lot of work to put this all together and to create this kind of authoring environment. I'm curious, I know you didn't present it in this paper, but have you done any work to maybe benchmark your current system against some of the packages that are commercially available that have kind of some similar purposes or functions or affordances? I'm thinking of there are some in XR, like Rockwell 3D Emulate, where you can upload CAD models and also dictate procedures. We obviously have PTC folks in the room here. With Vuforia Studio, I think you can also upload CAD models and either bring it into the tablet or bring it into the headset to enable work kind of accelerate how experts can actually capture instructions to give to more novice workers. And I know Tulip also has kind of a no-code platform for frontline operation workers. I'm just curious, have you looked at those systems, and are you able to comment on the differences between yours and what's out there right now?
Thank you. We have looked at, we've looked at these systems for inspiration and obviously for seeing what the state of the art is. We haven't benchmarked it in this work because this was more about finding the insights from the from the experts rather, and to see how they accept such a system in a workflow that is already existing. But we do intend to benchmark the productivity, I would say, or like the benefits of our system compared to these in the future.
Great, thank you.
Thank you.
Thank you. Other questions? Other question? Meantime, I have one. It's mostly more than one. So let's say that the one I think is more interesting for you. In real world, that is the topic here, from bringing the AR, VR in real world.
Mm-hmm.
So in real world, usually when you do maintenance and stuff like that, the parts are very damaged, dirty, oil and such things. So Do you think there is a way to consider this in your future work or in your actual work?
You mean that the oiliness or degradation is the problem, or?
Yeah, I mean, as it is a CAD model, okay?
Yes. Yeah.
There are a lot of situations where CAD model is representative, but not exactly what the final user will find in its way.
Sure,
so do you have a way to deal with this?
That's currently the challenge that we're trying to work out, which is, I guess, a 3D pose tracking problem in a sense, as the CAD models, as you said, they are representative, but often not, millimeter exact to what the real machines actually look like in the end. We're looking into this, and maybe, I can't say that we have a solution yet, otherwise it would be here. Okay. but it is a problem that we're looking at right now.
Thank you very much.
Sure.
Okay, a round of applause to Lucchas. Thank you. And we have a next talk, Error Management for Augmented Reality Assembly Instruction. The presenter is Anna Stanescu. Thank you.
Hi, welcome to my talk. I'm Anna Stanescu from the Graz University of Technology in Austria, and I would like to talk to you today about the work that I did with my collaborators and my professors, Peter Mohr, Franz Thaler, Mateusz Kozinski, Lucchas, Ribeiro, Skreinig, Schmalstieg, and Denis Kalkofen. So step-by-step tutorials in AR entails, as exemplified by, for example, this previous research, automatically detecting what the user is doing. And in an AR application with automatic progression, the user does not need to click a next button, and the object state is then continuously recognized so that the AR tutorial can automatically continue to the next step. And previously, we have investigated this in our work, and we presented, for example, this tutorial system that used the structure of the object state or assembly graph to improve the state detection for this automatic progression. But however, we did not handle what happens in the case where the user does not follow this assembly graph, so does not do these known states. So typically, this kind of tutorials follow a fixed sequence. And this fixed sequence models the progression of the object states like you see here in this image. So step 1 and step 2 are this fixed sequence, and then the AR tutorial takes that into consideration. But the users can deviate from this graph, and then they can make mistakes during the tutorial. And we propose an AR step-by-step tutorial application that can recognize plausible mistakes that the user make and can detect that mistakes. So you can see here in this video, a user is building a drawer and they see the next step visualized, and they actually mounted the white part wrong. And they mounted it in the correct orientation, and then they get a visual feedback that an error has occurred. And on top of the visual feedback, they also see a visualization about how to correct that mistake. So they get a visualization that they need to flip the white side into the correct position. And the user in this video does that. Then the system does recognize the correction and then moves on to the next instruction. So now with the green highlight, it moved to the next instruction, which tells the user to mount the part on the right side. So how do we do this? So for detecting these plausible errors, we aim to model them. So to model the plausible error states, and we aim to enhance the state graph by adding them as possible transitions in the state graph. So for example, here a plausible error would be mounting the screw at the wrong position in this step. So on the top side, there would be the correct position, and on the bottom side, there would be the incorrect position. So this is a quite likely error with reason in this case. And the core idea of our system and our pipeline would be first, generating this data with correct states and error states, so explicitly modeling them. Afterwards, we would train a real-time detector to distinguish between them, even when they have very small differences. And then we aim to also use the output of this detector directly in an AR tutorial application. So a bit about modeling these errors. So in related literature from more the production engineering domain, the users have been observed while assembling objects on a workbench, and the errors are categorized as illustrated. So this is a way to categorize them. So for this shown object highlighted in green, so this is an actual object from a data set that we used. We can see here the correct state that is expected to happen. And example errors would be like this, the dark gray pin can be mounted at the wrong location, or for example, the pink part could be omitted. The pink part could be in the wrong pose, so it could be rotated by, for example, 180 degrees, and this would be a wrong orientation error. The pink part could be mistaken by another similar part, and also it could be, for example, flipped because the object looks symmetric. And we consider these categories of errors and call them plausible errors that could happen during assembly. So for our experiments, to try out this error generation, we use two objects. The first object is a toy car. It's from a public data set. This is the one on the left. And another object is a furniture drawer. And then, using the Unity engine, we generate prefabs for each state in a state graph, and we also automatically generate the set of plausible errors for each state. So for this purpose, we assume that we know actually the object's mounting points. So these mounting points would be deduced before, maybe by assembly planning software or manually annotated by the user or something like that. So we assume that we know these object mounting points, which are highlighted in green here. And we also assume that the next parts are mounted perpendicular to these mounting points. So for example here, for the state 7 of this toy car, so it's just one state, this could be plausible mistakes where the pin's mounting position is varied in the range of close-by mounting points. So generating these errors can be controlled also by parameters that, for example, specify like how close do we want to vary the pin to the correct state. So further, after we generate this for the purpose of training a real-time image-based detector, we render images of our automatically generated states by using Unity Perception, which is a software for synthetic data rendering. And our goal is to use only synthetic data for training and real data for testing, and also, of course, real data in the AR application. And we generate this data and we perform domain randomization, and we vary the object's pose, the lighting, backgrounds, and also we add synthetic hands to increase the robustness in case of hand occlusion, which is the case in AR assembly. So when choosing the detector which was a state-of-the-art image detection neural network, which was YOLO version 9, which is a one-stage object detector with the architecture depicted on the slide. So this is a typical architecture of a one-stage object detector. And on top of the 3 losses of YOLO version 9, in order to distinguish better between visually similar samples, we also enhance it with a contrastive loss. So the contrastive loss has the effect of repelling samples from different classes while pulling together samples from the same class in embedding space. And here is also an example from our actual data from YOLO v9, so from synthetic data, and on the left side there's data trained without the contrastive loss, and on the right side there's data trained with the contrastive loss. So we can see that in the embedding space, this is plotted with the t-SNE algorithm, so in embedding space, or samples from the same clusters are actually pulled together. So this is the effect of the contrastive loss. And further, we also apply an enhancement that is proposed in related literature. So in our previous work, that makes the network be aware of previous states in the assembly sequence. So it's biasing it, predicting possible next states, and it increases also the performance. And these enhancements improve the network performance for this task. So We use these two data sets for evaluation. We use a subset of this industrial public data set, as well as the data set with the drawer that we generated, and we compare YOLO version 7 from related literature, and we compare it with enhancing YOLO version 9, only with the contrastive loss, of the state-aware module, and with the combination of these. And this improves the mean average precision when training with only on synthetic data, but also when training with adding a bit of real data, so 2% or 5% real data mixed with the synthetic data. So now we train this enhanced network with the synthetic data depicting correct and error states, and we predict the current state that the object is in. And we feed it to, we use as an input the real camera feed of a HoloLens 2. So at inference time, the contrastive loss is not used. It's only used during training, so it does not have any impact on the runtime performance. So here we show on the left the the output of the real-time detector. You can see the bounding boxes. We accumulate some votes over a few frames to avoid false positives and for more robustness. And then we show the resulting AR application on the right side. So this is from a third-person perspective. And again, we can see the example where the user mounted the white part of the drawer in the wrong orientation. Then the user actually looks at the visualization, and then they correct their mistake by rotating in a correct pose, and then the system then recognizes, again, the correct state, and the visualization is updated to the next step. So, as a conclusion, we propose augmenting an assembly graph by adding automatically generated plausible errors. We propose an enhancement with contrastive and state-aware modules to a state-of-the-art object detector. And we also introduce some synthetic data sets for this task and show a possible AR application for error detection. And in the future, we aim, so one of our main goals is to investigate how this application actually impacts the experience and performance of users. And as well as looking into error generation strategies that either do not model the errors explicitly or model the errors by learning from data directly. So, yes. So we present the AR approach for real-time detection, and our results show that it is feasible to implement such an AR application that learns from automatically generated data. Thank you for listening, and you can find a link to our project here with further details and about our research group, and feel free to also come and chat with me if you're interested in our project.
Thank you, Anna. So I think most of us find themselves in that situation, that mount the sofa and then discover that was mounted not correctly. So we are open to some questions. Thank you.
Thank you for the nice presentation. Stefan Lucchas, HitLab New Zealand. I have a question looking at the drawer. I think it's from a well-known flat pack furniture company. So what I normally do when I start to assembling it, I think I know better, and I jump several steps ahead just to discover that I need to go several steps back. So is this something you recognize as well?
Thank you for the question. Yeah, this is a very interesting question. So actually, the network can deal with this. So we trained a network. I mentioned that we use this state-aware module enhancement, and this biases the network to predict in the neighborhood. But we do train with a dropout strategy. So we actually, this has the effect that sometimes during training, this contextual information is left out, and sometimes it is trained with that. So yes, actually, the proposed network does deal with jumps in the graph. The current visualization, I think it can also deal with that, but that would be just an enhancement on the actual application side. But I'm fairly sure that the network does deal with that. Yes. Thank you.
Thank you. So we can have both, probably.
It's great work. And we do this for a living, and so just some thoughts and some ideas for you. But I love the idea of you digitally modeling all the possible error states. that works very, very well in constrained assemblies, very simple constrained assembly things. The errors that we see in real life of assembly are often subtle ones, like it's not quite pushed in properly. They're the ones that get you. So just a thought, and I don't know how it would fit in with your system, but as well as having your system model them, allow some real-time, real-work assemblies to then be brought back in to retrain the system. So teach you with some real examples of errors. So just some thoughts for the future, because I think this is excellent. So thank you.
Yeah, thank you a lot for your comments. So we did experiment with also adding some real data to the training. So I think this would be an ideal case, and also learning from this real observed data. We did not have this data in our lab, but would be definitely very interesting to check this out in the future. And when it comes to more subtle differences, we also have thought about this, and this could be part of our future work. One could, of course, model states that are closer to, like, less granular, so to say, or one can do some kind of outlier detection. So when you just actually take into consideration the correct state. And there has been some recent work in that direction, which is this paper, and this is also using contrastive loss. So it's a very, very interesting direction, yes, that we also plan to look into. Thank you.
Just a quick one, okay, please.
So I think with YouTube, we've seen like an explosion of, a community coming together. If I want to assemble something, I'll look on YouTube. And I was wondering how you see the evolution of this pipeline of kind of creating these instructions and people kind of contributing to something. Do you see this as, something that people will be able to build and kind of contribute to in the future?
Thank you. So you mean...
So kind of similar to how people would make YouTube videos. Would you see this as something that people can do at home for others to then kind of download instructions for when they assemble the same thing?
Yes, thanks. Yeah, definitely. So as an AR researcher, I feel like this is one of my visions and my motivators to do this kind of work. So I think the actual vision for the future would be that people would just grab their, or like already have their headsets and they just do it on the spot at home, or they just download another snippet for this object, or have some kind of assistant that trains them to do this. So yes, I think this would be a way cooler experience than following a YouTube video. So
agreed.
I think that would be
That's
great.
awesome.
Yeah,
Cool.
Thanks.
Okay, thank you, Anna. Thank you, and a round of applause for Anna, please. And we can go for the last talk of today. It will be remotely. The paper names Extended Reality and Digital Twin in the Oil and Gas Pipeline Industry, a systematic review on application, trends, and future directions. Please, can you put the presenter is Muskan Sarvesh. He will also answer question later by Zoom. Thank you.
Hello, my name is Muskan Sarvesh, a PhD student at the University of Calgary. Today I'll be presenting our work, Extended Reality and Digital Twin in the Oil and Gas Pipeline Industry, a systematic review on application, trends, and future directions. Over the last decade, the oil and gas pipeline industry faced challenges in construction, monitoring, and resource management. To address these, we propose using Extended Reality XR and Digital Twins DTs, which can greatly enhance training, safety, and system integrity, transforming how industry operates. Our related work spans several key areas in the oil and gas sector. We start with smart field technologies to improve data collection and automation, then building information modeling in oil and gas to streamline design and construction. We also looked at visualization tools and application in other heavy industries like manufacturing. Lastly, digital twins to transform operations in other areas of the oil and gas sector. We realized that although there are plenty of applications of DTs in the oil and gas industry, there is a lack of XR and DT integration in this domain. This paper aims to fill that gap by exploring their transformative impact in this sector. Our research focuses on three key questions: First, how our XR and TT technology is integrated into existing workflows and data management systems in the oil and gas pipeline industry. Second, what are the advantages and potential benefits of using XR and TT technologies in different oil and gas pipeline application scenarios? And finally, what are the trends or research outcomes that have been found or will be adapted in the near future to enhance efficiency in the oil and gas pipeline industry? Next, let's talk about the methodology. For our systematic review, we used the PRISMA method to gather keyword-based literature yielding over 2,000 initial records. After removing errors and duplicates, 3 authors screened the titles and abstracts, narrowing it down to 56 relevant records. After separating 10 literature reviews, we categorized the remaining 46 papers by scenario types for detailed analysis. In this presentation, we will focus on the first 5 classification categories that are scenarios, data collection methods, technology, experience evaluation, and hardware used. For more details on all categories, please refer to our paper. Let's review the high-level results from our classification analysis. We chose monitoring, training, maintenance, and testing as 4 scenario types. Monitoring focuses on real-time data visualization and situational awareness. Training supports workforce drills and safety simulations. Maintenance ensures equipment reliability, while testing evaluates equipment performance to identify functionality issues. These scenarios highlight a variety of use cases that demonstrate the impact of XR and DT in the industry. We focused on 3 data collection methods: real-time, using live sensors, pre-recorded, mostly through historical datasets, and mock-up or simulated data collected using modeling techniques. Since a significant number of papers emphasize monitoring, there is a crucial need for real-time data collection. This ensures timely responses and accurate decision-making. We chose 4 technology domains: virtual reality for immersive environments, augmented reality that overlays digital information onto real world, mixed reality which enables interactions in augmented and virtual environments, and digital twins as digital replicas of physical systems. Notably, the limited MR applications shows a lack of physical virtual interactions, highlighting a need for further exploration. Another category that we explored is experience evaluation, which focuses on human factors like user satisfaction, performance, and usability in XR and DT applications. As the graph shows, there is a significant lack of user studies, indicating a gap in research. The last category that I would like to discuss is the 4 hardware platforms used. We examined PCs, head-mounted displays, smartphones, and tablets. PCs are the most commonly used due to their strong processing power. However, there is a lack of use of wearable and portable devices like head-mounted displays, smartphones, and tablets, indicating a gap in the adoption of more mobile and accessible solutions. For our detailed review, we chose to dive deeper into the scenario category, focusing on monitoring, training, maintenance, and testing. In monitoring applications, we saw Lee et al. Demonstrate how integrating mixed reality with full-cycle digital twin systems in underground pipelines enhances spatial interaction, enabling intuitive visualization. Building on this, Staliandis et al. Developed a location-based augmented reality assistive system using GIS and global navigation satellite systems, specifically designed to manage underground utilities. Together, these examples illustrate how these technologies provide real-time data visualization, predictive analysis, and improved decision-making. In training applications, Andalus et al. Developed a VR solution to train operators in oil camps on different pipe scraping scenarios. Similarly, Santos et al. Created realistic simulations of oil platform training in VR to improve operators' understanding of hazardous environments and device locations. The takeaway here is that these technologies create an engaging, efficient, and effective training experience through data synchronization. In maintenance applications, Skoll et al. Used augmented reality for on-site visualizations to improve surveying and planning workflows, enhancing the efficiency of underground pipeline inspections. Similarly, Hertel et al. Developed an augmented reality prototype for gas pressure regulation stations, featuring expanding 3D models and digitized inspection form to identify requirements, challenges, and improvements. These examples illustrate how extended reality and digital twins offer continuous feedback and optimization strategies for safe operations in maintenance applications. Lastly, in testing applications, Lee et al. Used augmented reality digital twin systems with Boolean fiber optic sensors to assess and predict underground pipeline safety through an augmented reality interface. Similarly, Priyanka et al. Used digital twins combined with machine learning and prognostic algorithms to predict risk rates in oil pipelines, enabling timely failure detection and control through wireless communication. These innovations enhance situational awareness, visualization, and real-time guidance using data transmission and fault diagnosis. Through our systematic literature review, we attempted to answer three main research questions. First, we explored how extended reality and digital twins integrate into oil and gas workflows, identifying various use cases in monitoring, training, maintenance, and real-time modeling to enhance insights. Second, we examined the advantages of these technologies to improve accessibility to remote and hazardous environments, promoting safe training and supporting remote operations. Finally, we explored trends and future directions, noting that novel sensors and AI integration boosts predictive maintenance and operational workflows. However, these findings have also revealed several research gaps: a lack of physical virtual interaction, insufficient human research, and the limited use of wearable and portable devices. As XR researchers, we recognize that scaling these technologies will require better workflow integration and alignment with industry needs to truly maximize their potential. Thank you for patiently listening to our work. I'd be happy to answer any questions you may have now.
Okay, thank you. Thank you, Muskan. I don't know if you can hear us here in Seattle.
Yeah,
Muskan, hi.
you can hear me?
Okay, yes, perfectly. Thank you. So
Okay.
first I want to thank you that you give a light in a field which is very specific, not easy to know, and has also some important effect on society. Do we have any question here in the room? No, I don't see raised, but I have a question for you. In my knowledge of this field, which is very technical, there are a lot of rules and certifications. So even in devices themselves, they need to be brought on oil rig, stuff like that. So do you aware or do you keep this effect of regulations in your research? Did you find any effect? Any thoughts?
That is a great question, actually.
However, this research focuses on the applications of XR and DT technologies. I do realize that there are other areas of other areas in the oil and gas industry for training perspective, especially that require regulations and regulatory bodies, and that can definitely be a future work for us.
So in short, I was aware that they were not allowed to bring any HoloLens on. Yes, so I think, so when you say there is the need of devices, you mean also because of that, or you mean that for the specific industry there are some limitations that you are aware of?
I definitely believe that there are certain limitations when it comes to oil and gas industry. They're not very, they do follow traditional practices with PCs being the primary device of use, especially because of the convenience that PCs have in developing and testing the systems. Other than that, we have seen some papers that have been using head-mounted displays as potential solutions for training purposes. And we believe that augmented reality solutions such as using HoloLens or maybe even tablets or smartphones to reach inaccessible or hazardous environments would be a possible application for us.
Okay, great. I think we are done. Thank you, Muskan. I think you can address any further question offline in Discord. So with this, thank you. I want to thank you, the audience, for your attention, and we see you in a lunch break right now. Thank you.